we have to present is a recycle, a bike computer system. And this one has customers who are graduates from last year. So all of you who are graduating, I'm going to need plenty of projects for next year. So please think about supporting your alma mater with being customers for projects. So this is team number 14, recycle.
Hello everyone, I'm Ben, John, Brian, and we are Team Recycle. So I'm sure all of you are aware of just how many bicycles there are in, not just around the BU community, but in Boston in general. So we believe that the bicycle is becoming more and more an economic and legitimate form of transportation. So with this, we want to bring the bicycle into the 21st century. So what does that mean? We want to give to cyclists what modern day cars have had for decades. So we've created an embedded system for cyclists powered by clean, renewable energy. I'm sure most of you are familiar with what a cyclometer is, or a cyclocomputer. If you're not, it's just a tiny computer that you can put on your bike, and typically they track speed and distance as you're riding along. So our system is similar in concept to this, but we have a few more, we have more functionality. So along with speed and distance tracking, we have a GPS module and a heart rate module. So you may be thinking that's a lot of stuff to put on one bike. We've got the same thing. So one of our main objectives was to eliminate the need for multiple devices. So instead of having all these separate things on the bike, we've integrated all of these devices into one embedded system. And in doing so, we believe we've increased the situational awareness of the biker. And just going into the project, we estimated a final cost of around $300, which we stayed pretty true to. So this is just a high-level block diagram of our entire system. There's 3 inputs. The first input is user input, so we have a touch screen LCD, and so the user interfaces with our system using the touch screen. The second input is sensor inputs, so as I said, we have a heart rate monitor and we have speed and distance sensors. We'll go more into those later. The third input is what really defines our project. It's 12 volts AC pedal power. So we have a generator that's attached to the back wheel of the bicycle. And this generates the power that charges 2 main batteries that we have for the system. And again, we'll go into that later. The 2 outputs of our system is, the first output is what's displayed on the LCD screen after a user touches something that they want to see. And the second output is, so our system has a trips feature, which is similar to something you might find in a car. So say I want to take a bike ride from Photonics to Aganis. That could be one trip, and then maybe I want to ride Aganis to the East Campus or something like that. That could be another trip. So we have all these multiple trips stored in memory in our system. So you have the option of taking a standard USB drive. Plug it into our system, it'll automatically detect that, and you can choose to offload however many trips you want. You can offload 1 or multiple. And then after you have offloaded those trips, we have a PC application which you can plug in your USB drive into any Windows-based machine, run our application, and you can actually plot specific trips onto Google Maps. You can see the different routes.
So power generation happens in 3 steps. It starts with the bottle generator, which is mounted on the rear wheel of the bicycle. And as the tire spins, it spins the roller at the top, and that generates at maximum 12 volts output. And that goes into the charging circuit, which is the second step based on this NCT chip. And what that does basically is it protects the batteries from this unpredictable generator output. So that monitors things like the battery temperature, the battery level, and the amount of current that we're putting into the batteries. Then the third step is the switching circuit. We have two main batteries, both are 7.4 volt lithium ion. And at any given time, one is powering the main module. And if this battery gets too low and needs to be recharged, then it's switched via a series of MOSFETs and connected to the generator.
So next, this is the hardware that we ended up doing. We made a custom PCB, and there's also a breakout PCB that houses the GPS unit. So this guy will stream continuous GPS data and it will log it, and then if you do offload a trip, it will know which GPS data goes to that trip. So if we look, the custom PCB, there's two in-system programmers, so this is nothing is on this. We have two mounted boards and one unmounted. The main graphics processor is an Atmega 25600. It is 100 pins and it has 256K flash with 4K VEPROM, which utilizes to store the trip data. There's a bunch of debug LEDs, and then there's Watchdog AVR, which is an Atmega 644PA. Both can operate between 1.8 volts and 5.5 volts, however we run them at 3.3 volts with around 8 megahertz frequency depending on the function. And then this is all the power regulation. So there's 5 volt regulators, which are these 4 pin on the bottom. And there's also a 3.3 volt regulators for these 3 pins. The 12 volt, which makes sure that generator power coming in is in fact 12 volts, and that's step down to the things that we need. The way the power regulation works is these 4 pins have an enable, so the Watchdog controller can power up the entire board the way we want in a step sequence. It will first power on the Beagle Bone, which is going to be on the next slide, and that handles the GPS streaming USB functionality, and then it powers on the LCD screen, and this is incremented, and it waits for a GPIO line to go high, which are all of these. There's also GPIO lines going from this chip to this chip, and that lets it know that this is in fact powered on. If not, it will try and reboot the different chips that it needs to, depending on what's wrong. This is the GPS module. It mounts here to a right angle header. The GPS module needs to be perpendicular to the ground, otherwise you lose about half of the signal strength. If you lose half the signal strength, you probably won't get a location fix when you need it. So it needs to be mounted on right angle, and if you take a look at our project in the other room, it is in fact right angle mounted. This is the Beagle Bone. The Beagle Bone is a Texas Instruments credit card size embedded system. It has numerous GPIO lines that can be used for, I think there's 3 SPI ports, 3 I2C buses, and 5 UART ports, as well as everything could be a normal GPIO. It has a USB insert right here, as well as an Ethernet and then a 5 volt power with a 3.5 millimeter barrel cord. So we actually plug our 5 volts into this off of the PCB, and then this mounts onto the PCB right in with these over here. So that gives a stable connection, and then we can stream UART between all the chips and GPIO lines and things like that with Beagle. So the trips, what we're going to look at for trips are current speed, average speed, distance traveled, the time elapsed, your current heart rate, average heart rate, and the start date, as well as the GPS locations, which are streamed directly to the Beagle instead of to a different processor. What we're going to do here is, the reed switch is there's a magnet. It's the normal thing you see on a bike for a cyclocomputer. There's a magnet on the front fork, and then there's a magnet that also passes through, and it pulls 2 leads together, and then a signal is shot out, and that generates an interrupt in our graphics controller, which is also our hub for all our data. So that's interrupt driven. The average speed is based on the current speed. Current heart rate and average heart rate are done using a pulse sensor, so it's a little device that you put your finger on, and it uses a photodiode and takes ADC readings, and then it will find heartbeats using peak detection. The distance is also done through the reed switch, and time elapsed is only calculated as the system's actually on. So if, say today I started a trip, and then I shut the thing off, and I bring it up tomorrow, it will know that it is tomorrow. However, it won't say the trip is 1 day long. It'll say it's 2 minutes long, if that's how long the system was on. So it's just uptime, it's just power on time. So management options when you plug in a USB. You can offload a trip to the USB, you can delete a trip on the USB, you can view all the trips on the USB, and then on board, so if there is no USB plugged in, you can delete a trip off of the onboard memory, view the onboard memory trips, as well as start and end a new trip, obviously. And so if the system loses power midway through the trip, there's actually a protection protocol that will save the trip where it is into the EEPROM on the graphics controller. And then that way when the trip starts again, you won't lose all your data. So you have the data as it comes back to you, or right before it killed. So implementation. The onboard trip data is stored in the EEPROM of a graphics controller, which is the Atmega 25660. There's roughly 100 trips in our block structure that you can store, and because it's a 16-bit integer, you can have up to 6,553,500 years worth of trip data. The parameter that was put in place for a requirement was 20 hours, so I think we did pretty well surpassing that. There is a low power shutoff and restart procedure, so there is a real-time clock on the system that's handled by the watchdog it's powered by a coin cell, and when the whole system is not being powered or it has no main battery voltage coming in, it will keep the real-time clock going and going and going. If there's a restart, the watchdog will then tell the graphics controller what time it is, what date it is, and if the user says that's wrong, you can reset it and then it will reprogram the system with that date and time. The USB trip data, the USB, when it's plugged into the BeagleBone, directories will be put onto the USB if they're not already there, as well as some files to help with our file management system. There's trips, which contains the speed, average speed, average heart rate, distance, time elapsed, things like that. And there's also a GPS subdirectory that has all your GPS locations with date and time stamps.
So, as Todd outlined, the USB purpose is to document and save past trips or current trips, whereas the LCD is to feed live data to the user and allow them to manage these trips, as in move them from EEPROM to USB or delete them. So this is a basic outline of the setup we have right now. We have a 2.8-inch TFT LCD with a touch screen. It takes from an SD card to read bitmaps onto the screen, and the microcontroller is an AVR. It's an Atmega 328P. Unfortunately, we were looking to use a bigger screen, otherwise the screen meets all the core requirements we have, but we ran into some critical setbacks while testing that. We actually had multiple copies of the module that went wrong, so this is its own setup right now to demo the graphics, but it still needs to be integrated with the system because our current PCB has a header that was intended for the screen we're going to use that went wrong. So this is either going to take a little bit more work in software to adapt to the header that we have, the pins that we have available from the Atmega 2560, importing it from the Atmega 328, or potentially future changes to the PCB for a different LCD, or finding a similar LCD that would meet the header, since it's a pretty common format. Just a little bit about the LCD. It has an Ilitech 9235 controller, I believe, which takes a parallel 8080 interface. The screen we're going to use also takes a parallel 8080 interface, but it's slightly different because it's strange for some reason. It has its own frame buffer, and the controller is integrated into the LCD, so it's really well documented, it's really well covered, it's easy to interface with. So we have robust graphics. We don't have a way of taking data from the graphics controller right now. So really we just need to merge all the input from the sensors with the output to the graphics, which is just a matter of reading text, but we have our hardware linkage issues. But once that's resolved, we'll have a robust way for the user to interface with the system, aside from just shelling into it, since that's not really convenient for the common user.
So this is just what the PC application actually looks like. So written in Sharp in a document environment. So after you have offloaded trips onto your USB drive, you plug it into a Windows-based machine and start the application up. The image on the left here is the main screen. The application is just a logo and map name with all the file options expanded. We have select USB drive, trip route, clear map, and exit. The last two are pretty self-explanatory. So if you look at the image on the right, this is the select USB drive dialog. Here the user just enters in the name of their flash drive. It's simply for the application to find it. And if it is found, you'll be prompted with a success message saying, hey, we found the drive. If you can't find it, you'll be prompted include that as well, saying we could kind of. So the image on the left is the plot trip route dialog. So here you just enter in the number of the trip that you want plotted onto Google Maps. So if you have 5 trips or whatever on New Year's Eve Drive and you want to plot trip number 4, you just enter in 4. And then after you hit accept, you'll get this image on the right. This is just sample data. This is an example. So this is actually a trip that I took from Protonics, where we are now. We went down to West Campus, and we ended up in Stewey with a stop at K Center here. So this is just showing that it works.
So here's a breakdown of what we ended up spending on what we had implemented today for you. If we were doing a best case scenario, our number could be lower, but this is where we are today. Our PCB ended up being the most expensive, but in reality, if we had implemented the other screen that we had intended on using, our number would be lower.
So a big thing with this is an embedded system on a bicycle that's being recharged by the generator on the back wheel. So we needed to make sure this was as low power as we can get it. The reason for choosing an example of Beetlebone over something like a Raspberry Pi, which is making a lot of news, is that the Beetlebone is much lower power. The Raspberry Pi draws about 500 milliamps continuously, while the Beetlebone in idle mode is around 130 milliamps, or 170, depending on what you're running on, if you have the USB insert and stuff like that. So these are just some basic, what everything's running on. Everything is regulated down from 2 lithium polymer batteries. So with how much 750 milliamps we're drawing, we can have this guy run over 3 hours with the 2 1,500 milliamp hour batteries. So when we did test it, I tested it the other day without the LCD screen. It lasted over 8 hours, and the real-time clock has been, I just today actually, when I was getting this ready for the demo later, I had to change the real-time clock coin cell battery. So I've been testing with that since February, continuously. So I think the requirement was 5 days to keep a real-time clock, so that was also well surpassed. So the casing, it's made from 1/8" polycarbonate. There's a sliding debug level, so you can bring everything out of the system if you need be, and you can also raise and lower the PCB on its platform with 4 screws with 8 hex nuts. All the batteries go down into the bottom level of the case, and then this guy slides off so you can get into those batteries. There's also a hole on the top, and if you can see slightly here, there's a USB hole where you can plug the USB in. One of the stipulations for the project was to be able to get everything off of this device and get it off the bicycle quickly. So the way to connect all the peripherals to the device, including the heart rate monitor, the reed switch, the generator, that's all done using SMA connectors, which are usually for TV. However, they have the inside connect and the outside, and so we were able to connect everything that way, which unscrews very, very quickly. So these are some side views of the connections. So right here, the heart rate, the sensing, the ADC line, is a connection by itself, and then there's power and ground for that, and then also another one for the reed switch. And on the side, this is the generator plug-in, and then they feed right into the circuit board right here. And once again, the batteries are stored underneath. The case was designed by a mechanical engineer, it's actually in fact Jerry, and it was machined in the BU machine shop. So future improvements. Instead of using EEPROM for the graphics controller to store trips, it would be better to use flash memory because it's much more reliable, and the EEPROM on the AVR is limited to 100,000 read writes. So yeah, that's a lot. However, I'll probably hit 1,000 testing, and over time, if you wanted to use this for years, it would not be a good idea to use the EEPROM. Also, the graphics controller can be eliminated. We can plug all graphics right directly into the Beaglebone because it's meant to do that in the first place. It's much more robust. We eliminate room on the PCB, which would in fact lead to a shallower casing and a much more better looking system. Professor Hornstein?
I have 2 questions. Can you go back to the slide that shows the box mounted on the bike? I don't understand how it gets mounted.
We have been haven't figured out a way to mount it actually. There's different ways that we know there's possibilities. One way was to create screw holes into the bottom of the case and then take some rods and then connect them that way. Another was to have slits in the main part of the case and slip through some rods and then screw them on. We haven't found a definitive way to mount the
It
neck.
looked like a bicycle frame was going through your plastic box. Bring back that, what are those big things? Those big black cylinders?
Here,
Yeah.
that's shrink wrap over wire.
Oh, okay, so with your hands, how big is this box?
That big.
Okay.
That's the top, and then it's probably about that big.
And my second question is, the generator you're using brought back fond memories of my youth. I had one of those on my bicycle to run the headlight. And I remember it being much harder to pedal when the little generator was hitting the tire. So my question is, do you have any data or estimate on what the human power to electrical power output efficiency is of that thing?
Not exactly, no. We haven't been testing with pedaling. It was just a requirement that the car be supplemented. There wasn't really a number on how much it had to be supplemented, so we don't have data on that.
So, where did you get that thing? They still make them?
Amazon?
They still make it?
Yeah.
I'm shocked. Anyway, thank you.
And so it's a really cool project, and it made me realize I don't know anything about what products exist in this market. So
Yep.
it made me think, what products exist and how you compare to those. And particularly if I had an iPhone and a heart rate monitor watch,
Yeah.
how would it be better than that system?
So one of the competing technologies is Garmin actually creates something very similar to this. However, it's not rechargeable. It's a small little, maybe 2-inch screen that actually gives you live tracking with their GPS, and you can also wear a Garmin heart rate monitor. So it's quite similar to that. However, it's not rechargeable. Or ours is rechargeable, theirs isn't. So that's the big difference maker. As far as an iPhone, we were actually considering making this a Bluetooth thing and streaming directly to the phone. However, we wanted to go the Linux route and do kind of our own custom system. So, in my opinion, I would say it's actually more feasible to do something like that. However, we wanted to create something that was all-in-one and that didn't have the different peripherals going in completely different directions. I don't know if did that answer your question?
Yeah, I think if you were to commercialize it, there'd be more rigorous questions
Absolutely.
to be asked, but I think for us, the project is pretty cool.
Okay. Yes.
Is there any limitation between the day and night when you use that because of the touch screen as far as the user is concerned?
It's resistive. Are you talking about brightness? Actual brightness?
Yes, right.
Yeah, we didn't get to aim to sunlight readability just because we ran into these issues with the screen. We figured if it came down to it and it was a problem, we found a website that makes adjustable sizes for a film cover for a screen that's supposed to really help with sunlight readability. And we figured in future revisions, if we wanted to upgrade the screen, we could go to OLED too, because that's supposed to be better in sunlight readability. The reason we chose LCD is because our screens are mostly static images with just text changing or only part of it changing. And LCD is supposed to last much longer than OLED for that. So for the purposes of this project, we figured it'd be better to start with LCD. So.
Another follow-up question also about in case of safety of your device, what are the measures that you take? Because most of the time it happens that something goes wrong and you have an accident,
Right.
plug into the brakes and how fast it would be.
Well, initially we were thinking of including a maps feature on the screen itself with live feeding like a GPS, but we figured that would be too distracting, and we had initially planned that if the user is going over 4 miles an hour or some very low speed, since we're detecting that anyways, we would just put the screen to a static clock or something like that. But since we limited the amount of data we're actually showing live, we figured it probably won't pose too much of a threat since it's just essentially showing a speedometer while the user is moving, and that's available in the car as well. So we don't think it would be too much of an issue, but in terms of commercializing it, we definitely have to look into that further and maybe still take the same initiative where if they pass over minimum speed, we'll just go to a static clock or something like that to minimize distraction.
Sort of one of the safety issues. Can you think about maybe using voice commands or some way to interface with your device instead of them having to take their eyes and hands off of what they're doing?
Yeah, we definitely did consider that, but that kind of felt like a different project in itself too. But it's definitely worth considering for future revisions too.
Thank you.
Everyone.